Okay, we'll make a start. Good evening, everyone. Welcome to the fifth lecture. We're at the quarter waypoint. The fifth lecture in this series on history and philosophy of science and 20 objects. Last month and this month, we're covering a pair of objects which between them are kind of emblems for that extraordinary transformation in natural knowledge and its status between roughly 1550 and 1750 that comes to be remembered as the scientific revolution. This is the period when observation and experiment become bywords for the scientific method. Last month, it was observation's turn. Our object was a microscope, and we saw in the lecture that a range of skeptical challenges have been raised from Robert Hooke's day right through to our own on whether seeing truly is believing when we use microscopes, whether we can trust the world as we apprehend it through even our most amazing instruments, or whether we're always doomed to doubt. So that was last month. This month, we turn to experiment. Our objects are these rather magnificent air pumps from our collections. Nothing less than the laws of nature, whether there are any, whether we can know them if there are the targets for the skeptical challenges to come. They'll be raised by my dear colleague here at Leeds, Stephen French, Professor of Philosophy of Science, aided and abetted by Dr. Mike Finn, who's the director of our museum. So over to Mike and Stephen.
I'm on. Okay, thanks, Greg. And welcome to the lecture. So, air pumps then. We have three examples here to look at. Now, this one in the middle is the one that was used in the pictures, the adverts. This is called a Hawksby air pump. It's named after Francis Hawksby, who was Isaac Newton's lab assistant in the early 18th century. So the design is about 300 years old, but this model is about 175 years old. This is the oldest of the three then. So it's it's double-barreled here. I was going to say like Tara Palmer Tomkinson, it's vacuous and double-barreled. So we have here a bell jar sitting on top, and when we turn this, right, here's a little bit of thing. So we create a vacuum in the middle here, and when we turn the handle, we would turn the music down because sound doesn't travel through a vacuum, and the sound would disappear gradually. Now, I control the volume there. We weren't actually creating the volume. I have to admit, like David Attenborough, I don't want to get into trouble. As a curator, we don't want to risk the glass here because it might crack under the pressure. So we've got two pumps here. Then the second oldest design here is this Tate's double action pump. So we've only got one barrel, but with two pistons inside, and we move that backwards and forwards to create the vacuum. And then the third design we have here is Floyce's. This is the most fun design, and we sort of crank this up and down and create to create a vacuum in there. Okay, so these are three designs. This one is from about 1850s, and this one from about the 1890s. What we might also have added to any of them, so on this point here, for example, is a mercury barometer to not only create a vacuum, but to measure the pressure inside as we go along. And that's going to become important in what Stephen's talking about. So those are the three air pumps there that we have. So these are sort of interesting, but to start off thinking about them, they seem maybe a little bit mundane, they're maybe not as exciting or immediately important as the microscope that we looked at last time. But I think, like the microscope, they are just as crucial as instruments in that period of time that we call the scientific revolution, when natural philosophy grew. And like the microscope as well, the air pump owes a lot to Robert Hooke, that figure we looked at last month on the left-hand side here. So he who wrote the Micrographia was the giant on whose shoulders Isaac Newton stood. So the air pump, it's an invention from around about 1649. A German inventor Otto von Guericke develops an air pump for mining, but it's not a scientific instrument so much. Around 10 years later, Robert Boyle, who we'll hear more of, takes the air pump and says, let's turn it into a scientific instrument. And Robert Hooke is his lab assistant, his technician. So we've got pistons and barrels, we've got bell jars, mechanisms. It takes a lot of skill to make these. It takes the gun maker's skill, the clockmaker, the glass blower, and it also takes a bit of strength. On these, it's a nice smooth pump action. On the original, it would have been a crank, so that the lower the pressure went, the harder it became to move. And it takes the real skill of a technician like Hooke to get these things to work. And the air pump becomes emblematic of the early Royal Society, that institution founded in 1660 in London, where gentlemen come together to discuss discoveries and to talk about science and improved knowledge based on their great inspiration, Francis Bacon. So knowledge to them is to come from organised common sense. And experiments are there as part of that. Experiments create matters of fact, sort of momentary truths about the world that we can trust and that we display in front of other people. So everyone sees us create this experiment, show this effect, this phenomena. People can go away and recreate it in their own time and prove that it was real, that it actually happened. And so experiment changes in this early modern period. It goes from being something, if we think about the alchemists looking for the philosopher's stone, it's not a continuous process that never ends. An experiment becomes a discrete event, and it can fail. It can fail or succeed. So why would they develop the air pump? What were they interested in? So early in the century, in the 1620s, William Harvey had discovered circulation of blood in Oxford. He showed blood flowed in a circulation around the body. And at the lungs, something seems to come out of the air that's necessary for life. Something to do with the springiness of air. But what is that? What gives air that springiness? Well, Boyle's great idea is if we want to understand what that thing is, let's take it away. We remove it to understand what it is and what it does. So we create a vacuum. We remove that springiness. And it's seen that the same thing that enters the blood, when it's taken away, it causes flames to be extinguished, or it causes life to be extinguished in animals. So this is an important instrument of biology, but it's also an important philosophical instrument. So for years, people have debated whether or not a vacuum is possible in nature. Aristotle said no. Galileo says yes. Descartes says not really, you can't have a vacuum. This philosopher, political philosopher Thomas Hobbes, gets into a wide-ranging debate with Boyle about this because he doesn't think a question like whether a vacuum can exist can be answered by an experiment. It's a philosophical question. It's an issue of metaphysics. But Boyle shows, well, actually, we can use an instrument, carry out an experiment to show that you can create a vacuum. There's a very famous book by Simon Schaffer and Steve Shapin called The Life of an Airpump, which details this debate. And then 100 years later, we get the air pump still being spoken about. It remains contentious and important. In a book on the airs, Priestley wrote, "The English hierarchy, if there be anything unsound in its constitution, has equal reason to tremble even at an air pump or an electrical machine." So I'm a big fan of Joseph Priestley. I've heard him described as the Jeffrey Boycott of science, but more importantly, he's the inventor of fizzy pop in Leeds. So he's a really important man. But he's also somewhat of a political, religious radical. And he says, well, instruments give us truths about nature, and they help us reveal God's truth. And if any kind of political establishment tries to hide that from us, they're in danger because this reveals what the truth of the world is. So that's Priestley doing experiments down by the canal in Leeds. And around about the same time, too, one of my favourite paintings, an experiment on a bird with an air pump by Joseph Wright of Derby. Here we've got an air... It's a bit dark, it's not very visible. One of the most famous images in science. So here we've got the experimenter standing over... Can people see that if I make it a bit darker? Standing over the air pump. And you can see in the middle there's a bird. So the moment's captured while the bird is still alive, but the experimenter's there turning the handle. So that bird's going to die because the air's going to be removed. So we see the power of science, the power of the scientist over nature, the control he has. But also we see that the air pump is not just about experiment, but about demonstration. It demonstrates science and educates people about science's effects and the effects of nature. Okay, so at that point, having shown what a kind of important instrument the air pump is in lots of ways, I'm going to pass over to Stephen. There we go. Cheers.
Right. Okay, thanks, Mike. So, I'm really not going to talk about the air pump very much. I'm going to use it as a kind of hook on which to hang the following questions. Two kinds of questions. One, really fundamental question for HPS, for all of us, I think. How does science work? Okay. What is the nature of the scientific method? Quite a tricky question. Not going to be able to go into it in very much detail in the time I have here, but I do want to consider the sort of following on question, well, is science observation-led or is it theory-led? Okay? And then I'm going to get quite metaphysical, move into the area that's become known as the metaphysics of science. Recently, it's kind of grown in interest, and a lot of people working on this, to look at the question, what is the nature of the laws of nature? What is a law of nature? Are they universal? Do they govern? If they do, in what sense does a law of nature govern? Okay, so that's going to get quite metaphysical, so hold on to your seats. Here's Boyle again. Born in Ireland, as a young man, travels around Europe, as you do, becomes infused with the new natural philosophy, as you do. After his father dies, moves back to Britain, settles in England, and with the money from his estates in Ireland and England, builds a lab, as you do. And as Mike mentioned, Hook is his lab assistant. And in that laboratory, he does the work for which he has become well known. One, he's well known for founding modern chemistry, and perhaps to the dismay of some of you, I'm not really going to be talking too much. Well, there'll be a little bit of talk of chemistry, but I'm going to be talking too much about that. He is taken to have pioneered the scientific method, and that's partly what I want to talk about. What do we mean by the scientific method? And he discovers, in some sense of discovery, Boyles Law, the relationship between the pressure and volume of an ideal gas. Okay, pressure is inversely proportional to volume at constant temperature. And I'll be talking a little bit about that. Now, there is a sort of tradition, a view, that sees Boyle in a lineage that goes back at least to Bacon. Okay, Francis Bacon, again, sometimes referred to as the father of the scientific method. I think all I knew at school of Bacon was that he died stuffing a chicken with ice. He was very interested in cold, the temperature, how to preserve things. But he is regarded as one of the natural philosophers who emphasize empiricism, the empirical method. Okay? Actually making, so just relying on what your predecessors had said in the books of Aristotle and so on, actually making careful observations, adopting a skeptical and methodical attitude towards those observations and one's scientific work. And so Boyle, in using the air pump, okay, is regarded as setting his work on the air pump, his observations, in what's called a natural history of the air. I mean, why the air? A colleague of mine just this afternoon, Chris Kenny, who actually does know a lot more about Boyle than I do, said that Boyle was fascinated with the air. Why? Why? Well, because, as Mike indicated, it's the air that gives us life, but it's also the air that can power things. Air has power, it has springiness, right? And Boyle was very interested in this, how you could use air in pumps to do things. What's the law of that? What's the relationship between the various quantities we're measuring? By natural history is usually meant something Baconian. Okay? Vast collections of matters of fact derived from observation and experiment which provided the foundation for natural philosophical theorizing. And that kind of framework naturally suggests that for Boyle and for others, the scientific method consisted primarily, or at least initially, in making observations, careful observations. Leads to the suggestion that science is observation-led. Okay? And here are some of Boyle's observations, and I mean, a lot of this you can get online, and they're really meticulous. He records all his observations, and you can see, I've just pinched that off some wiki page, the relationship between pressure and volume for an ideal gas, encapsulated in Boyle's laws. Okay? So, one view of the scientific method that Boyle is reputed to help establish and advance is that it's observation-led. Okay? So, you find this in popular media, you find this view espoused by scientists themselves. What distinguishes science is observation-led. You find it in the Oxford English Dictionary. The scientific method is a method or procedure that has characterized natural science since the 17th century, the scientific revolution that Mike and Greg have talked about, consisting in systematic observation, measurement and experiment, and then the formulation and testing of hypotheses. Okay? But, and here's a gratuitous picture of Albert Einstein. Einstein had a very different view. A theory, he said, can be proved by experiment, but no path leads from experiment to the birth of a theory. That suggests a very different view. That suggests the kind of view that's sometimes called, by me as well as other people, a eureka moment view. The eureka moment goes back to Archimedes. And again, a bit of a caricature. The view is taking a bath in ancient Greek, as he did, and as he sank into the water, and the water lapped over the bath, he discovers the laws of buoyancy, leaps up, little naked middle-aged Greek guy running through the streets shouting, "Eureka! I've discovered it! I've discovered it!" It's the light bulb moment view of science. It's the view that science begins with these light bulb moments, these hypotheses, these theories, and then they are tested. They're either proven in some sense by experiment, or they're falsified by experiments. That's a very different view. So here it seems we now have two contrasting views of the scientific method. One that seems to go back to Boyle, observation first. One that at least Einstein seemed to espouse, that it's theory-led. Okay? And we find, again, in popular media, this theory-led view being presented. So here's a scene from Big Bang Theory. Sheldon Cooper on the left, theoretical physicist, right? Leonard Hofstadter on the right, experimental physicist, basically regarded by Sheldon, the theoretician. Leonard is basically regarded as a lab monkey. Okay? The theoretical scientist comes up with theories and laws through flashes of inspiration, inspired guesses, whatever. All right? The monkey in the lab, test it. Right? Aye, Captain. Runs off, test the law. Yes, it's proven. No, it's falsified. Okay? Again, I mean, for comedic value, brilliant, great. Lots of laughs there. Is the true picture more complicated than that? Yes, of course it is. Go back to Boyle. Did Boyle, having set up this laboratory with his own, Hooke, lab monkey on hand, right? Robert Hooke, right? Do this for me, build me this equipment, aye, aye, boss, right? Did he then just start making observations? No, of course not, right? You've got this expensive lab, you're not just going to sit there and go, oh, I'll just start making observations. What of? Right? Oh, everything. No. Boyle was already bothered by claims of a Jesuit scientist, Franciscus Linus, that the pressure of air, the springiness of air, was actually insufficient for it to do all the things it does in fact do. So that there was something else going on. Boyle thought, no, that's not right. And he was also aware of the following couple of guys, Townley and Power. Henry Power, I think actually, can't remember where he was born, but he set up shop as a doctor in Halifax, took these new bits of apparatus, the barometer and so on, went up and down Pendle Hill and measured how the pressure of air changed as you went up and down the hill, in case you went up and down different altitudes. And Townley not only corresponded with Boyle, he met Boyle in London. And indeed, Boyle refers to this relationship between the pressure of air at different altitudes as Townley's hypothesis. Poor old Henry Power kind of got the raw end of the deal because it was actually really his hypothesis. But once Boyle had called it Townley's hypothesis, that was pretty much it. So Boyle already had something in mind, some hypothesis, some idea, when he performed his experiments. So to say that Boyle's law, the discovery of Boyle's law, was in some pure sense observation-led doesn't quite tell the whole story. The role of observation was not so much, but the role of observation here was not really to prove, this is going against what Einstein says, not really to prove Boyle's law. It wasn't the case that Boyle woke up one morning and thought, oh my God, pressure, it's inversely proportional to the volume at constant temperature. Who would have thought it? No. What the observations did is to give Townley's hypothesis some precise shape and form. And it's worth noting, and we can talk about this in discussion if you like, that even Einstein, who insisted on this kind of flash of insight view, even Einstein utilized certain kind of experiment, a thought experiment, to arrive at his theoretical claims. The special theory of relativity did not spring into Einstein's head again one morning when he woke up. He wondered, as a young man, what it would be like if you ran as fast as a light wave. And he thought, well, if I run as fast as a light wave, according to Newton's mechanics, the relative velocity between me and the light wave is going to be zero. So the light wave is going to appear stationary. Right? If you could run as fast as a car, going at 40 miles an hour, the car would appear stationary. But Maxwell's theory of electromagnetism, light is an electromagnetic wave, tells you that a light wave is a set of oscillating electric and magnetic fields. So it can't, turns out, it can't be stationary. So there's a problem there. And that thought experiment, that thinking what it would be like in that sort of situation, led Einstein to think, actually, I need to change the whole basis of space and time and move away from the Newtonian picture. So the conclusion of this part of the talk is that the relationship between theory or laws and experiment or observation is actually quite complex. It's not a matter of either starting off with observations, nor is it a matter of just coming up with a hypothesis. It's a complex interaction. And it's fluid. We should not expect the scientific method understood in this much detail to remain the same throughout history. Certain platitudes will, right? But there are vast differences between what Boyle was doing and what Einstein was doing, and what post-Einstein physicists have been doing. And teasing out those differences is, I think, one of the more interesting and enjoyable parts of history and philosophy of science. Okay, now let's consider the second part, the second sort of hook to hang on the air pump. The nature of laws. Okay, here are some laws. Okay, F equals ma, Newton's second law, force is mass times acceleration. Or Newton's law of universal, note the word universal, law of universal gravitation. the force between two masses inversely proportional to the square of the distance between them. G is the gravitational constant. Other kinds of laws we find in science, I haven't put them up because it starts to get too many symbols, but Schrodinger's equation governs all quantum phenomena, well, all phenomena actually, strictly speaking. Einstein's equations of GR, right, tensor equations that relate the mass-energy distribution with the structure of space-time. These are laws that are often cited by philosophers as the kind of thing we talk about when we talk about scientific laws. They have certain characteristics, okay? They are universal, right? Like the Ten Commandments, they're expected to apply to everything, okay? They govern, in some sense, the phenomena. And they are robust. In what sense? Well, some things can change, right? Can change my sweater, change the colour of my socks, change the distribution of people in this room. I can't change F equals ma. I can't change Newton's laws. You can try and fight the law, but as the Clash found out, the law will win. Okay? So these are the characteristics of laws that philosophers in particular often ascribe to them when they're thinking about Newton's laws, for example, or Schrodinger's equation, or Einstein's laws. Okay? Boyle's law is different. There's a reason why we call it the ideal gas law. And Boyle's views on laws were actually quite interesting. Boyle was very careful to take his law to apply, first of all, only to air. Obviously, at that stage, this is pre-Priestley. There wasn't really any understanding of the composition of air in terms of different gases. But Boyle says that this law, it applies to air, only applies to the measurements made within the limits of the experimental setup. Even more interesting for those of us who are into this stuff, Boyle, in this rather complicated statement, says three things. He says, first of all, the matter out of which this universe is made could have been different. Second thing, the initial conditions that this universe started with could have been different. And really interestingly, the laws of this universe could have been different. Not only that, the laws could be different in different parts of the universe. So the laws should not just be taken, they're just assumed to be universal. Okay. So thinking about Boyle's law, right, the ideal gas law, pressure is inversely proportional to volume. What do we mean then when we say it's ideal? Well, it applies within a certain regime, within a certain range of pressures and volume. If you go up to higher pressure, you start to see deviations from that law. If you go to lower temperature, likewise. If you get closer to a phase change where the gas starts to condense into liquid, liquid becomes solid, that's a phase change, the law breaks down. And as I'm sure some of you in this room know better than I do, these deviations are described by something called the compressibility factor. Now we can model this deviation from the ideal law towards the real situation by de-idealizing features of the ideal gas model. What's that, the ideal gas model? Well, Boyle's law, as it's stated, is concerned with volume and pressure, certain macroscopic quantities. But of course, people from Newton onwards were very keen to ground the law in some sense in the emerging picture of the world as made up of microscopic constituents, atoms. Newton tried to do it with a model of atoms as static, explained some aspect. It wasn't terribly successful. It wasn't until the 19th century with the kinetic theory, the idea that gas, air, is composed of atoms, molecules banging around, that we had, as it were, a kind of microscopic model on which Boyle's law could be grounded. We have something called the ideal gas model. And it's ideal in the sense that the molecules or the atoms are all taken to be indistinguishable from one another. They're all taken to be hard, typically infinitely hard spheres, right, with zero volume. The collisions between them and with the sides of the container are elastic, so no energy is lost through friction or whatever. They're subject to Newton's laws. There are no long-range forces acting. There's just these immediate collisions. Okay? And this is often presented in the form of an analogy. The gas atoms are like billiard balls. I mean, the snooker series is just finished, so I thought that would be appropriate. This kind of model, known as an analogical model, and this kind of analysis of models, is most closely associated with Mary Hesse. Okay? And she was a lecturer here at Leeds in the maths department back in the day. She was a founder of History and Philosophy of Science here at Leeds, and she subsequently moved on to become professor at Cambridge. She did many things in her career, produced many great works, but I think for me this is a classic. I think for many other people working in this area, models in science, how scientists use models, the kinds of models. Her book from 1963, Models and Analogies in Science, remains a classic. And she broke down the analogy between atoms in the ideal gas model and billiard balls into these three components. There's the positive analogy. Okay? Billiard balls, like gas atoms, they have mass. They're very hard. They're not infinitely hard, but they're very hard. They're spherical, more or less. They obey Newton's laws, more or less. Negative analogy, gas atoms don't have colour. Chemists have assured me about that. Neutral analogy, however, was where Mary Hesse thought all the real interest should lie. Okay? Playing billiards, you notice that the collisions are not perfectly elastic. There may be frictional forces, other kinds of forces. So one might then be led to speculate, is that the case for gas atoms? And it was in the neutral analogy that Hesse located, really, scientific development and scientific progress. It was by exploring that neutral analogy and basically taking aspects of that neutral analogy and placing them in either the positive or the negative category that she thought science typically progressed. The kinds of idealizations that we're talking about in the ideal gas model, infinite hardness, for example, are sometimes called Galilean idealizations. They're deliberate distortions of the actual situation. I don't know if this was the actual inclined plane that Galileo used or, actually built in 1973 by a PhD student, but it's kind of similar to the plane that Galileo used. And rolling objects down this, thinking about the motion, Galileo speculated, right, what would it be? What would happen if the plane were frictionless, if no energy were lost through friction? Right? That kind of thought leads you to think, right, if there were no friction, the ball would just carry on going. Right? If there was nothing acting upon it, the object would continue to move. It's that kind of thought that leads to, for example, Newton's first law, that objects, unless they're disturbed by forces, will continue in a state of rest or a state of constant motion. But here's the question, here's the philosophical question. What do these analog models that Mary Hesse is talking about, that involve these idealizations, what do they tell us about reality? Okay? Think about Juha Saatzi's talk from last month. If you're a scientific realist, if you believe that scientific theories are more or less true, that the things that they refer to, right, exist out there, what do these idealized models tell us about reality? They're strictly and explicitly false. Okay? So how can we be a realist about them? Well, there's an obvious answer. As a realist, you can say, look, they approximately represent, more or less, to certain degrees, in certain respects, certain general features of the world. And, crucially, the claim is made, they can always be made more realistic by de-idealizing right, by moving away from the view that the gas atoms are infinitely hard, that the collisions are always elastic, and so on. Okay? And again, you know, there's people in this room, I'm sure, that know about this much more than I do. There are real gas models that scientists have used. Van der Waals is one that I learned at school, but there are others invented. I think the Payne-Robinson one may have been the 1940s. I don't know. Anyway, I don't know my history of recent science on this. These are, I think maybe the Payne-Robinson one was invented by engineers who were concerned with, you know, gas flow and gas movement and so on. But all of these models incorporate these sort of de-idealizations. They move closer to reality. So the scientific realist can say, look, it's all right, don't worry about it. We may use these idealizations for various reasons. We may use them because it just makes the model simpler to use, and we can capture certain aspects. We can understand Boyles Law using these models. And then when we move to pressures that go beyond what Boyle thought of as the limits of the experimental setup, we'll use one of these other models. We've always got something more realistic to hand. So we don't need to worry. Okay? So we can always de-idealize. Well, can we? First of all, there's a problem. Turns out that there are some idealizations that we apparently can't get rid of. When we consider phase changes, like gas to liquid, for example, these are quite often modeled by taking the thermodynamic limit. What does that mean? It means take your gas in here and imagine it's made up of an infinite number of particles. Turns out if you do that, certain devices, you're enabled to use certain devices, right, that make the model, well, explanatorily much more tractable. You can explain the phase change. You can do things with the model. Right? But then if you say to the realist, but don't worry, because the realist is going, oh, what are you doing? Thermodynamic limit? No, gas has an infinite number of particles. Don't worry, we can just de-idealize. You can't. Because if you de-idealize, if you move away from the infinite limit, you lose your explanatory power. That's a problem. This is a problem that it's a current problem in philosophy of science. How then are these models, how do they explain anything? There are people in this room who are concerned with this problem. And also it turns out that actually scientists don't behave the way, do they ever, as realists would want them to. Rather than going through more and more real models, right, typically at some point the scientists go, for God's sake, it's too complex. I'll just shift to a different model. To hell with the ideal gas model. There are billiard balls now. I'll do something completely different. So there are issues there for the realist to consider. Just to wrap up, recall the characteristics of laws that I set out. One, they're universal. Well, not all laws are. Right? And those of us working in the history of science should pay attention to that. Not all laws are like Newton's laws or Schrodinger's equation, applying to everything. Some, like Boyle's Law, have a limited applicability. And there are interesting issues to do with that. But what about governing? So here's an image, sorry, I didn't label it, of, I think it's a Sumerian king receiving the laws from one of the gods are god of judgment. The source of the governance there is the god. What's the source of governance for the laws that govern phenomena? For Boyle, it was clear. As a theist, it was also God. Okay? We get this notion of law from, well, the laws of the land. What's the source of governance there? Well, it's a kind of social contract. We all agree, I would hope, I'm looking at you very closely now, that we will obey the laws of the land in exchange for peace, safety, security, and so forth. Right? But what about the laws of nature? Where do they get their governance from? Why should phenomena obey them? For Boyle, again, it's God that is the ultimate source of governance. Well, here's a very different view. Fast forward, not very far in the great scheme of things, but fast forward to the middle of the 18th century, and there's wee David Hume, looking very stylish, in his turban and his waistcoat. Hume thought that laws simply don't govern. And this view has been further articulated by one of the 20th century's most famous metaphysicians, David Lewis. And this statement here is often referred to as the statement about the Human Mosaic. All there is to the world is a vast mosaic of local matters of particular fact. Just one little thing after another. As the politicians might say, just one damn thing after another. There are no governing laws imposing order on things. There's no governance, there's no necessity to the laws. It's just the way the world is. And that what we call a law, what we call Boyles Law, P is proportional to 1 over V, is just a description of the regularity in the world. It's just a description of this mosaic. So there's a mosaic, right? We have these patterns in the mosaic, we have these regularities. All that are statements like Boyles Law is a statement of features of the mosaic. It doesn't govern them, doesn't impose its will upon them in any sense. But then there's an obvious question. We say, well, hang on a minute, not every regularity gets the accolade being called a law. There's a big difference between Boyles Law and French's law. What's French's law? French's law, and this I will tell you now, is a true empirical statement. At any given time, Stephen French has no more than £15 in his wallet, much to the dismay of his friends and family. Okay? Now, that may be of interest to French's friends and family. Most of us would not call that a scientific law. Most of us would not deem that to be sufficiently interesting to be a scientific law. What makes, if all that laws are descriptions of regularity, how can we pick out certain regularities as laws? Well, the answer of Hume and Lewis and their ilk is that these laws, these descriptions, feature in our best system, our best theory. The theory of Stephen French's monetary habits is not a best theory. It's not very interesting. In particular, it has very little strength, very little explanatory power, and doesn't have much in the way, many people say, of simplicity. The best system is a theory that balances strength and simplicity, explanatory power and simplicity. And the statements, the descriptions of regularities in the world that feature in our best systems are what we call laws. There's an obvious worry here. How do we balance strength and simplicity? That makes it seem a bit subjective. It makes it seem as if what we call a law is a subjective matter. There's a further worry, which is that once you move into quantum physics, you get connections between these matters of fact that apparently can't be handled by this, or can't be accommodated within this human view. But there are people in this room who are also looking at that and how we might extend the human view to accommodate that. Now, that's just one view of laws in the metaphysics of science. There are many others. Let me just sort of start to conclude by sketching one of the alternatives. And the reason I'm sketching this is because it's partly, or largely due really, to James Ladyman, also once of this parish. He was a PhD student here, now professor at the University of Bristol. And together with one of his collaborators, Don Ross, he's articulating a view in which the world is not a Human mosaic. The world has a structure to it, and laws are patterns in the world. In addition to the matters of particular fact, there are relations connecting these facts. There are patterns connecting up the regularities in the phenomena, so that what we have is less like a mosaic and more like a kind of interwoven rug. The laws don't govern things in the sense of imposing themselves, okay, in the way that the Ten Commandments are imposed, right? We should stop thinking of the laws as standing over the phenomena. Rather, we should see the laws and the phenomena as interwoven, such that we can't really even understand what it is to be a phenomenon in the absence of the law. They're tied up very tightly together. And in their book, Everything Must Go, they articulate this kind of view. Again, there are other views out there, happy to talk about them in the discussion. I just wanted to give you a taster of the different approaches to this question. What is a law of nature? Okay, back to the air pump. Well, or the Large Hadron Collider. Same thing. Devices such as the air pump really brought in, as Greg indicated and as Mike articulated, a new era. Observation became rigorous, became controlled via experiment. Laws began to be formulated, Boyles Law, Newton's laws, and so on. Okay? In the 21st century, the devices and the laws are much more complex. The standard model of elementary particle physics, recently confirmed by the discovery of the Higgs boson in the Large Hadron Collider, is a much more complicated set of laws and symmetries. But many issues remain the same. What's the relationship between experiment and laws? What's the nature of the scientific method? How does science work? And what is the nature of these laws? How do they feature in reality? Okay? How do they relate to the phenomena? In what sense do they govern? These issues all are still in play today. And it's these kinds of issues that those of us working in the philosophy of science, among others, are interested in. Right, I'll finish there. Thank you.